Hello, my name is Nicholas Schell, and I'll be showing you the complete process of utilizing XFOIL to find the coefficient of lift versus angle of attack, coefficient of lift versus the coefficient of drag, coefficient of lift over coefficient of drag versus angle of attack for three airfoils, the NACA 0010, the NACA 4410, and the Epler E385 airfoil. So to start, I'm going to go to command prompt. All right, so my name is Nicholas. I'm just using my buddy's computer. So CD, execute this file. All right. So we will start with the NACA. Let's do the NACA 00. All right, as you can see, it's got all the parameters here. 160 panel nodes. That's okay. We'll keep it that way. Panel bunching parameter, we'll keep that. Let's do the density ratio. We'll change that over. So EAR. We'll show you the configuration of these panels. We can change the density. So now we'll do T. 1. All right, so now it's set to 1. We'll keep the panel nodes at 160. It makes it simpler. Right. So as you can see, I changed right here. 1. All right. Next, let's do the operation. Let's do Reynolds number of 375,000. Okay, as you can see, it's right there. Then let's do a sequential angle of attack from -5 to 20 with an increment of 1. As you can see, it's starting to print out all these coefficient pressures. As you can see, the angle of attack as it increases, you got a coefficient of lift, coefficient of moment, coefficient of drag. All right, well, it did not converge. So what we could do to fix this is you can go back and go to PPAR, go to and increase the panel nodes, which is that could be a possibility. Good. All right, as you see, panel nodes 200. All right, and then do upper. And let's change the iteration to 100. And then we'll run this again. Better chance of converging. Sequence halted since previous 4 points did not converge. All right, so it stopped at 12. Or no, stopped at 16. Sorry for that. All right, well, if we were in a hurry, which looks like I am in a time crunch, I'll continue. You keep going, iterize it. You can do a iteration of 200 points. and then run it again, see if you get any closer. But what you could do, since it converged right there, it looks like 16, it got the last one. So you could do 18. Should get something, you should get to 18. Let's see. It may not converge. Looks like it's not going to converge, but no worries. I already did this, and I will just show you what I did. So once this stops running, you want to get all these points. You're going to have a total, was it 25 points? So -5 all the way to 20, and you would want to save your polar file. Write PPAC to save and write your polar file. You save it, and then you want to open up Excel and go. Well, I have it already set up here. So for this one, I opened it up. I got 20 points right here, -5 to 20, completed. And I copied and pasted what I found. And then this was for Reynolds number of 375,000. And then this was the Reynolds number of 1,250,000. So I copy and pasted this one and that one. And then I differed these plots for the coefficient of lift versus angle of attack, coefficient of drag versus angle of attack, and coefficient of lift over coefficient of drag versus the angle of attack. As you can see, this was for the NACA 0010. Obviously, do it again, run it all again in XFOIL, and do the same process. Save the polar file, and go to your Excel sheet and copy and paste another data set for the NACA 4410. This one was Reynolds number of 375,000. As you can see, I only got to 18 to converge, so I just kept it that way. It's very difficult to converge on XFOIL. But again, on this one too, it looks like -5, -4 would not converge correctly. So it was -3 to 18 would converge. So as you can see, the difference in the plots from Reynolds number of 375,000 and Reynolds number of 1,250,000. Higher Reynolds number gave you a higher coefficient of lift, it looked like. Coefficient of drag was lowest with a higher Reynolds number. throughout the angle of attack increase. And then this seems to be true because coefficient of lift over coefficient of drag. If your coefficient of drag is low, you're going to have a higher coefficient of lift over coefficient of drag ratio. So as you can see, Reynolds number of 1,250,000 is your higher ratio. And again, for the this thing's still going. Sorry, I shouldn't have done that many iterations. If this ever happens, you just exit out. Bang. All right, and then we'll open it up again. I'll show you how to open that file. I went on to UI, I think it was UIUC. Let me see. Yeah, right here. UIUC, yep. It's the airfoil database. Copied the E385, which is right here, Epler E385 airfoil. Copied this data. It was data coordinates, and I put it in the command prompt here. Let's see, I put it in XFOIL, not command prompt. Sorry. All right, so let's do this again. Execute. All right, so we wanted to load a file, so we want to load that data. To do that, you just press load. It'll say enter file name. For this one, I just named it E385.dat. And there it is, with all the panels. I did the same exact process. It took a little bit of fiddling around to get it to converge properly, but I got it. I think I kept the panels. I think I kept them at 160, which is like the base value. Oh no, looks like it's 34. Let's see what we can just check. Oh, it's 160. Yeah, right. That's good. And we kept it there, and I changed the density ratio to 1. Once you got all those points, all this situated here, parameters situated, you do the same thing, run the sequence from -5 to 20 degrees angle of attack, and document that data. Do the PACC polar save file. You save that, go back to Excel. For this one, it's right here. And yeah, I couldn't get 16 through 20 to converge, so I had to deal with this -5 to 15. I got some good plots though; they look pretty good. It follows the logic. So as you can see, Reynolds number 375,000. This is all 375,000 Reynolds number, and then this is Reynolds number 1,250,000. Coefficient of lift, coefficient of drag, and CL over CD, which we wanted. Plot them, see the difference. Again, as you can see, there's a trend. There's a higher CL with a higher Reynolds number. Again, a lower CD with the higher Reynolds number. And again, the ratio is higher for a Reynolds number of 1,250,000. Okay, and then once that is established, just you completed that assignment, that first part of the assignment, and the XFOIL portion of the assignment. So we'll be moving on to the next part of the assignment, which is XFLR5. So let's open that up. All right, so we got it open. We're gonna do new project, and then XFOIL direct analysis. Oh, sorry, this thing is in the way. Can't see it. There it is. All right, now I can see. Sorry, this screen sharing thing is in the way. Let's get rid of this. Let's go back to the foil. We can get a foil. Foil design. All right, here we go. So now let's choose a foil. For this one, we're going to do the 0010 foil. Why it's doing that? That's NACA 0008. Keeps on doing that. But for this one, we're going to call it 0010. All right, so there's a 0010. And then we're going to call another foil name. And for this one, it's going to be the 4410. And we'll name it 4410. And then we're going to open our data that we got from the E385 UIUC website, which, as you can see, it's right here. So just going to copy that. It should post right there. It is. All right. So we got all three foils on here. Now we can run the analysis on this. So just go to XFOIL direct analysis. And what made it easier for me is I batch the analysis. So I can do all three at one time, foil list. You want to highlight these all three so it shows that you're going to do all three at one time. Make sure your list is correct. Okay, so I already had it set for Reynolds number list. It's going to run it for one at 375,000, and the second one will be 1,250,000. Okay, and then I already did this, but I'm showing you again. So alpha -5 degrees, max alpha will be 20 degrees, and the increment will be 1. Let's do iterations. I was doing high iterations so I can try to get this to converge, but I was having trouble. So let's increase it to see if we can converge any further. Let's analyze it, run the data. We should start to see it plot. I guess not going to plot. Oh, there it is. Okay, there's one. It'll probably take a bit because it looks like it's running the Epler airfoil first. It's already done the Reynolds number 375 and Reynolds number 1.25, which is good. It's going to continue on. Well, a lot of this unconverged, so I don't know if you saw that. You can see some unconverged parts. There's unconverged. It's 0. 500 iterations couldn't converge. Yeah, the XFLR5 has a tendency of doing this. So, I mean, if you increase iterations, it takes longer, more accurate though, but it takes way longer. So I guess to speed up the process, since I already did this, what you would do is you go to polars, export all polars, and save it into a file, which in this case, since I made a whole batch of them, I just saved it to a batch file. And then I sent it over to my Excel from, let's see if I can find it. All right, so here is the NACA 0010 XFLR5. I believe I might have already shown this, but I mean, it's been a long day. But again, do it the same thing you did at XFOIL. You just plot them for the coefficient of lift versus alpha. The assignment asks for that. Let's see if I can show you the assignment so I can verify that I was doing it correctly, which I should be. Here it is, yeah. CL versus alpha, CL versus CD, versus CD, and CL versus CD versus alpha. Okay. Okay, and then once you do that, you go back to the, yeah. So it looks like I might have made a little mistake, but I'll change it. It's supposed to be CL versus CD. CL versus CD here, sorry. But this is just as rough. It looks like I did this again. But yeah, kind of the same process. It's quicker. XFLR5 is way quicker. But the thing is, it just has trouble converging at some points. But you can see we got some, there it goes, it completed. So let me move this out of the way. All right, so here's your CL over alpha. Kind of looks like the plots I showed you earlier on my Excel files. CL over CD ratio over alpha looks just like the ones on Excel. Same data points. This is the CL over CD, which we wanted, which I will change. And moment coefficient over alpha, which is we didn't really need that for this assignment. But this is great software to know. I believe XFOIL was made by MIT. It might be made by the same school. So very cool though, very cool software. But yeah, that's the assignment. I didn't have enough time really to continue on and go for the bonus. I would have tried, would have loved to try this, but as you can see, I'm on crunch time, get this turned in. But yeah, all right. Well, thank you for watching.